All right. Ah, now I got the red dot. Now I see the red dot. Okay, so we're recording. Okay, so we talked about what's not done in the decode stage. First of all, are there any questions about what we did last time? Something that was not clear, or you want me to repeat? No. Okay, so I'll go ahead.
Yeah, maybe just give a recap or no?
Yeah, well, I can look at this. Well, a recap of everything. It would take me the entire time that it took me.
Yeah, the most important stuff.
Well, let's look at this picture. Look at this picture. Well, I think an important thing to remember here, if you're looking at this picture, is that this when you see this line here, it means that there are physically connected 5 wires. I mean, they're tiny, tiny wires, but there are 5 wires going into the read register from this spot in the command. In other words, the command is in the data section, right? It's in the data section. There's lots and lots of commands in the data section. But in order to run the command, we first have to move each one, that command that we want to move into a register. We can, I don't know what the name of it is. Maybe it's like, we can call it the command register, the register that holds the command. And that register has special wires connected to it. And that wires are like this, that these 5 bits here are connected directly to this spot. And these 5 bits here are connected to this spot. And these 5 bits are connected to this spot in the register file. This is the register file. This is this box which enables us to read and write to our registers. So if it's an add command, we don't have to do any deciphering of what number is here. We just put the bits. If it's written here 6, then the bits of 6 are put here, and the register file knows which register we want to get it, because those bits are lighting these things up over here, and these bits are lighting. We don't have to read it and then make a decision. Oh, it's 6. We better go get 6. This register file is built to read whatever is on this line, and whatever is on this line is whatever is on this box, and whatever in this box is whatever you put there in the command. So it just automatically works. And then, of course, the read will go through here, and the other read here will go through here. I'll add them together, and the result will come out over here and be written here. That's my recap. Is that good, Yitz?
What does shamt and function stand for?
So shamt stands for shift amount, because there's a command called shift left logical and shift right logical. Sometimes we want to shift something, and if we're shifting something, we put that amount here, like for how much we move to the right or to the left. And if you think about it, then what's the maximum you could move? Well, the maximum you can move is everything off, and there are 32 bits, so the maximum you can move is 32. So all you need to be able to write here is 32 or 31, let's say. But there's this. You're not going to ever do shift of 0. Shift of 0 is meaningless, right? So it doesn't do anything. But shift of 1.
So what does it have there if you don't want to shift?
What?
So if you don't want to shift anything, what would it have there if not 0?
Well, of course, in order for it to even look at what's here, in order for the ma'abed to even relate to the, obviously there are wires coming out of the shift amount, and there are wires coming out of the function amount. But where do they go? They go somewhere else. But if it's a shift command, if the opcode over here says it's a shift command, then he's going to relate to what's here. But if it's not a shift command, then really he's just going to ignore what's written here. So we just write 0 there. But I don't think that 0. I don't think if you wrote. I think if you wrote something else there, it would also work just as well. I don't think there's any significance to it being 0, because you're just not relating to it. That's why in this picture, in this diagram, if it's an add command, he didn't draw the wires coming out of it because it's irrelevant. They're going somewhere, but they're not. We're not going to do any action based on what's there. I mean, you can also ask, why isn't the opcode anything wires coming out of that in the function code? We for sure need those to know, in fact, that it's an add. Well, the answer is there are wires coming out of it. I didn't draw that. How did that get there? Anyway, there, it disappeared. There are wires coming out of this and coming out of this, but they're going to something called the controller. The controller, which is deciding what command it is, basically. I'm not really deciding, but it's doing whatever is written there.
So
Anyway.
there's another kind of black box where op, shemp, and function go to.
Yes, exactly right.
Okay.
And I'm calling that black box the controller, and we're going to talk about it later.
Okay.
A lot later. But right now, assume that the computer just knows what to do, knows that it's an add, and therefore it relates to whatever on these lines. In this we said, he says, neither have we read the function field to know what ALU command to do. In other words, he's saying like this, we do know, at this point, the controller has looked at this and knows that it's an R type because he sees it's a 0 here. And whatever R type it is, he's going to take this register and this register and this register and put them in. But the ALU, to decide what to do in the ALU, he's going to have to look at the function command. Does he want to do subtraction or addition? If it's subtraction, it'll be a different number in function than addition, for example, or whatever. There's a lot of possibilities. Whatever possible thing he wants, the function is going to be connected to the ALU. But we haven't yet done the ALU. All we've done now in this stage is read these things, and their data has gone into the ALU, and the ALU hasn't yet done its job. Okay. Now we're going to say, in the same stage, what would we be doing if it were a different command? For example, if it would be a load word. We just explained, remember there are 5 stages, and I think we're in stage 3. Go up. We're in the decode stage, maybe that's stage 2. We talked about this a while back. Here. Well, that's funny. He calls the decode stage here. You don't even see the decode. But we're basically accessing registers. We're in that stage, the 3rd stage. We're basically talking about these first 3 stages. Anyway, let's go back to the work. The stages are not so important. It's really not important to know the stages because we're in single cycle, and everything essentially is happening in one cycle. So it's not really, we talk about stages, but it's all in one clock tick. So how is the question? No? Okay. How is the load executed? Assume we have the command load word 809. Did we discuss this last time? Maybe we started to discuss it, no? Okay. Suppose we have that. This means that RS is 9 and RT is 8. We did discuss this. The value 8. So wait, so let's go to the picture. Here. Here's that same register file. And remember, keep in the back of your mind what we're doing. We're doing a load word. So, oh, by the way, are you guys having a Mayor Komar immediately after me?
Yes, we are.
Yes, you are. Okay, so I'll give you 5 minutes to get a glass of tea. Read register, write register. Look what it says: RS9 and RT8. That 8 and 9 are coming from over here. Sorry. There's an 8 and there's a 9.
I just want to mention something. The sound is quite crackly.
Oh, that's just my microphone. I could maybe use a headphone set, and then you'd get a better sound.
It just got a lot better. I don't know why.
What?
It just got a lot better in the last like 20 seconds.
If I go over here, is it better? Or if I go over here, is it better? I don't know where my microphone is. Or if I go here, is it better? There's my microphone. Is this good?
Yeah, that's good.
Okay.
I think so.
I'll try to talk slowly and loud. So here's an 8 and here's a 9. That's the command I want to do. This is the 9. Can somebody tell me what the 9 represents?
Register 9.
Register 9, that's true. But what value, what is the meaning of the value in register 9?
Isn't it like the place in the array that you go into? Like the, what's it called? I forgot the name, but like when you go into the array, the 9th spot.
No, close, very close, but no. This is a register. This is not a number. This is a register. It's not the 9th spot. This is a register which has 32 bits in it. And that register of 32 bits is something. What is it?
An address?
An address. Thank you. An address of what?
Looks like an array because we're shifting 100 spots into it.
Yes. And the beginning, theoretically, the beginning of an array. That is the pointer to the array. And 100 is the offset. That means of that array, go 100 places forward. And if it's words,
That means
25 places forward, because it's words. So that's the pointer. That register is the pointer. I need to find out what's in that register in order to go there and get the information and then plug it into 8 and make 8 be, I'm writing to 8. It says my internet connection is unstable. Wait, I want to see what my kids are doing. Just a second.
Yeah, you gotta unplug the Xbox,
Guys?
all that stuff.
What are you guys doing? What are you guys doing? I think your food is ready. Yeshua, food is ready. Sorry, they were not using the internet, but anyway. Okay, so the 9 is telling me where to go, and the 8 is the location that I want to store. Load word means to copy from that location into register number 8. So let's look at the picture. So the 9, wait, let's go back again. Remember this? 9 is the pointer. That means I need to take that 9 and read. It's the read register. I want to read. I want to get that 32 bits so that I know where to go. I need to know where to go. Right? I need to go to that location. So I need to read it, and it's going to come out on this line. I put it into read register 1. Notice that this is a load word, which means it's a I type, which means there's only 2 registers. That's why you see a register here and a register here. What about register 2? No wires connecting it. Obviously, there are wires connecting to it, but we're ignoring them. In fact, we're going to look at this 32. Actually, what's going to happen is the instruction register is going to have multiple sets of lines coming out of it. Multiple sets of lines coming out of it. In other words, it can either send the first 5 bits here and the next, sorry, obviously the 6 bits at the beginning are the opcode. We're not talking about that right now. But the next, after the first 6 bits, then the first 5 bits after that can go here, and then the next 5 bits can go here, or the next 5 bits can go here, depending on what we're interested in. Now, there's different highways. There's a highway connecting the first 5 bits to this, and there's a highway connecting the first 5 bits to this. So if it's like a train with train tracks that have a switcher. That has a switcher that can tell the train, don't take this track, take this other track. So the first 5 bits are going to go now here. Notice the first 5 bits are going to go here after the 6, and then the next 5 bits are going to go here. So what have we got? The 6 for the opcode, 6 for this register, 6 for the opcode, 5 for this register, 5 for this register. And how many are left? 16. There's the 32 bits. Where do the other 16 go? Look at this line. Down here, 16. See the 16 there? That means that 16 bits have come into the sign extender. So now we figured out where the operation register, the instruction register, where it's sending its data. So the 9 is going here. We're reading what's in register 9, and we're getting out 32 bits. 32 bits is, again, we said, the meaning of those 32 bits is a location in the data memory where the array is sitting. So, but we have to also incorporate, that's not enough. We could theoretically just take those 32 bits and put them right into the address here of this is the data memory, and get out on the output the content of that location, which is what we want. But we have an offset to think about. So the offset comes down here in 16 bits. It goes into the sign extender black box, and that black box is going to turn it into 32 bits. Now the 32 bits go here into the ALU, and the ALU is.
Wait.
Did I disappear?
Nachum, a part of it? Oh,
What?
there.
You did, but you're back now, which is nice.
Yes.
Either way, so is that circuit just for the load word?
Wait a second. Yes. Kind of, yes. Hey, what's this?
I mean, that circuit isn't used for anything else other than the load work function.
Share, wait a second. Oh, I'm still recording. I don't know what that means, but if it's 2 recordings or 1. Is that circuit used for just, yeah, well, what we're gonna see is like, basically, it's really very similar to a train station, to think about train tracks. We need to get, like every train needs to be able to get to every station, but not, sometimes this train is gonna, if I go out north from this train station, I'll turn right, to I don't know, Tiberias. Sometimes I'll turn left to Haifa. So there's a switcher that switches that controls whether the data is going to the right or the left.
So it splits at that instruction at that first branch here on the circuit.
Yeah, well, actually, I'm thinking about it. The truth that wait a second. Right, there's a switcher. So the switcher will tell it. Now there's tracks laid from the instruction register to register right. And the reason we don't see it in this diagram is because the controller has switched and sent those bits somewhere else. So the person who drew this diagram just showed you what is the reality after the switch has been made, after the switcher of the train tracks has done his switching. He's not showing you all the tracks that are not being used, but they're there. You understand? Does that make it clear? In other words, this picture and this picture seem to contradict each other. Because here it says that the second 5 bits go to the read register. And in this picture, the second 5 bits, which is the RT, the same RT, remember this is RT. RT is always this second 5 bits. RS is the first 5 bits and RD is the third. But now we're in a load word command, which has no RD. And these last half of the word is the shift amount, or not shift amount, is the offset. True? Give me a thumbs up. True?
True.
Yeah, I'm with you.
So this is the offset. But this RT is, according to this diagram, is connected to register 2. But according to this diagram, it's the same RT is connected to not read register 2, but to write register. So which is it? Can't be both. The answer is it is both. It's got tracks connecting it to that and to that. And there's some kind of master controller who's telling him which tracks should be used, which tracks should be active. And how does he decide? Based on what the opcode is, based on what instruction it is. So this diagram is not showing you all the wires, it's just showing you how the wires are being used.
But if we want to continue with the metaphor, this could potentially be the only train station, as it were. Like all the operations could be done with this diagram, just we don't see all the wires. Like I think that's what just like was asking.
Yeah. This is like, it's like exactly. This is my connection. It says my internet connection is unstable. I don't know why. I'll tell you why. Because the entire country is on Zoom right now. But yes. This is.
Are you using Wi-Fi or internet?
It says my internet.
Are you using wireless connection?
I don't know. You have a pretty good wireless connection.
Yeah.
I think I have a pretty good wireless connection. I don't know. I don't want to start looking at it now. Nothing I can do about it if it's bad, so forget it.
So
yes, Yona, what you said, yeah, I agree with that. Say it again.
That this is essentially where all the operations are done. It's just the controller tells which wires to light up. But this is one theoretically. Maybe there's probably more.
Yes, this diagram and this diagram are the same. You say, wait a second, but there's no data thing here. There's no, remember, this is 2 pieces, and this diagram has 3 pieces. Because what about this piece, this data memory? The answer is this data memory is over here also. The guy who drew the diagram just didn't write it in because it's irrelevant. It's irrelevant for this picture because even this picture is not full. Even this picture is not full. The only full picture would be the entire computer. But we don't want to throw at you the whole diagram of the whole computer at the beginning. So we're starting with pieces by pieces. And as we're adding to it. First we did
So that load that.
Yeah.
So that load word picture, it's the same circuit. It's just highlighting just the cables or wires that are currently being used for that function.
Well said. Well said. That is the same physical object. It's just we're highlighting where we drew in those lines which are actually being used at the moment, and those lines that are sitting unused are just not drawn, but they're there.
Could there be multiple register RFs and LUs in your computer, or does this one RF do all the instructions you give it?
Excellent question. There's just one RF. Theoretically, there could be. There's just one. There theoretically could be two, but there aren't. I mean, there's no reason to have two. We'll see, though, that sometimes there are duplicates. We'll see that in different versions, we'll see sometimes there's two ALUs. Sometimes there might be multiple ALUs.
Okay.
RF, very unlikely you'll have multiple. I mean, if you can't have multiple RFs. Logically, you can't. If you'd have multiple RFs, then you'd have multiple sets of registers. In other words, if I would have another RF, then I wouldn't have 32 registers. I'd have 64 registers. This is the actual register is actually in there. Just like this data, the actual data is in there. That is the.
Can't you make an RF of less than 32 registers?
You can make an RF with any number of registers, yes. I mean, usually a multiple of 2. Irrespective of the length of the registers. You could have an RF of 64 registers where each register is 32 bits long. No problem. Totally reasonable.
Oh, I had a quick question about the sign extender. We had talked about it in one of the previous classes at length about how you can only move a certain amount. But I was wondering, just technically speaking, it seems like because the sign, the offset and all that go into the ALU, is it true that it'll really add only 0? And then because the ALU is adding the two together, is that the reason why it only can go to that area of memory?
Well, I didn't hear everything you said, but I think you're asking is, do we really need a sign extender, essentially?
Oh, no, we definitely need it. But because it's going to go to the ALU, is it just going to add all the zeros or only ones, and the ALU will add them together?
Yeah. The sign extender, yes. If this is the value -1, which means it's all 16 ones, then what's going to come out of here is 32 ones. Which will still be -1, but in a 32-bit form. And then it'll stick that into the ALU, and the ALU will do its magic, and it needs all those 32. If it wouldn't extend it, then it would be 16 ones and then 16 zeros, presumably, or it would be blank. It would be 16 zeros, and then it would give you the wrong result. So if this is -1, it's going to have to extend it to all ones, and then it takes this number and this actual location and this offset and comes up with the new location. So that's exactly where we left off. So that's a good question because it keeps me going forward. That's where we left off. We extend it. We get 32 bits here. We get this address here that we got out of the ALU represents the actual location within the array that I want. And it's an absolute location. It's somewhere in this 4 gigabytes of data memory. It's an absolute location. And I plug it into the address, and the data memory spits out the value at that location. That value, we never discussed exactly what this looks like, but it doesn't matter. That value comes out, goes along this wire, goes here, and comes into the right data. Well, that's what we want to do, because we want to write it to where? Let's go back at the command. We want to write it to 8, register 8. We want to go to register 8. So we get to, in order to get to register 8, we're going to have to use the RF, the register file. So we go back to the register file, and we're going to write this to 8. Well, how do we know to 8? Over here, we connected the original instruction. We took its RT section and connected it to write register. So that's where that's what tells it where to write. Is that clear? Can I go on? Thumbs up? No? I'm waiting.
Myself.
You guys see me?
Yes.
Sorry about this. Share screen. Okay. Sorry, my internet apparently is throwing me out. Okay, so did everybody give me thumbs up if you are okay with this diagram? I got some thumbs up. And if you are not, then speak now. I want verbalization. Okay, good. So that is the operation of this. I mean, basically, you know, if you think of the gadol in general, what are we doing now? We are teaching you, I'll say it like this. We're teaching you one thing, how to read a diagram. That's really what we're doing. Once you know how to read a diagram, then all this is obvious. In other words, right? If you think about it, you don't have to really know anything. You just have to understand what's written here. This is a new language. What
We can read the diagram, but does that mean you showed us earlier what's in the register file, what's in the ALU, and what's in the data memory, but does that, if we know how to read the diagram, are we still responsible for what's inside the register file, the ALU, and the data memory, like all the logic gates, the multiplexers, and decoders, and things like that?
Yeah, is there going to be a question on the exam? Please draw a diagram of the register file. I think it's I'm not writing the I'm not writing the exam, but actually I think that's a legitimate question. I actually think that's a legitimate question. Draw the diagram of the register file. I think that would be a totally legitimate question. I mean, I wouldn't want you to just memorize it, but you should be able to work it out from first principles. You should be able to figure out, well, there's got to be a read. There's got to be a read. These 5 bits have got to go somewhere. Where have they got to go? They got to go to the registers. So there's got to be 32 registers in here. And they got to go to all the registers. You got to. It all makes sense. There's no 2 ways to do it. There's only one way to draw it. It has to be the way it was. So you shouldn't memorize the register file, but it should make so much sense to you that you could draw it if you needed to. It's not like memorizing the periodic table of the elements, where they're just, you got to know the names and the number of protons, and this is actually it's derivable by first principles. So I think it would be a legitimate question to ask you what it is. I don't think I've ever seen an exam where they ask that question, but maybe I'll put it on. I don't know. I personally think it's a fine question. The teacher might say it's too easy because you can just memorize it. But the questions are going to be more like, I'll tell you what the final questions exams will be. They'll be like, what change would you need to make to the circuit so that you could support the new command that I'm inventing? I am inventing a new command that does this. How would you change the diagram so that it could support this command? What new wires would you have to add? So that's more creative. That's more creative because you can't memorize that. You have to just know what the diagram works, and you have to think, okay, what would I do? Anyway, now we're going to talk about the branch command. We did. I mean, you can see where this course is going. we're going to go through all these. That's why you have to learn these commands, because we can't talk about how they physically work unless you understand what they're supposed to do. So branch, if you remember, it says jump. What does this mean? It means jump to location 25 if what the value in A8, register 8 is equal to the value in register 9. True? That's what that means. If these two are equal, then jump to physical location 25. Now this example, they wrote physical location 25. The truth is, in the lab, that's illegal to go to that location. It's too low down. It's a very low down place. And actually, it's problematic because 20, well, is it problematic? No, we're going to add 2 zeros. Remember, 25 doesn't really mean 25. 25 means 25 and then add 2 zeros to it. So it's going to be times 4, it'll be 100. Because it can't be, you can't jump to a something that's not ending 00. That's not a multiple of 4. 25 would be an illegal address if we really wanted to go there. We can't jump there.
Would you need to put a hexadecimal number there?
No, the way he's writing this, no. This is a decimal number. He means to write 25, but he's writing it the way the kidud is. If you would write this in code, in other words, if I would write branch, if this equals this, go to line 100, that would be a mistake. Even though you wanted to go to line 100, you would have to mentally remember, oh no, I got to divide it by 4, and you'd write 25. But on the simulator, you're going to write 100. And the simulator will automatically divide it by 4 for you and put it into 25, so that when the processor runs it, he'll change it back into 100.
The simulator as in like Mars?
Yeah, when you use Mars, that's what I'm calling the simulator. When you use Mars, you'll write 100. I mean, usually you won't even write 100. You'll write a label here. You'll write location like end or jump or loop start. But that will be translated into an address. But it won't be translated to a number. But it won't be translated into a number. It'll be translated into a number and then divided by 4. Because the chip is built to multiply it by 4. I'm just saying, in Mars, theoretically, you could write 100 here. And then the kidud of it, the encoding of it that the computer would actually see wouldn't be the 100 that you wrote. It would, the simulator would change it to 25. Again, that's a thing that Grace Hopper, presumably did to make our lives easier. In other words, you want to think I want to go to location 100. You don't want to say, okay, now I got to take out my pocket calculator and divide it by 4 and write in 25. You just know what line you want to go to, so you put on a 100, or you put it. It's not going to necessarily 100. It could be 10,452. Or I don't know. So then or 54, and then you're going to have to divide that by 4, and you get some number. So instead of doing that, you just write it in automatically, and the simulator divides it by 4. But really, what we call the kidud, the encoding of your command will be 25 if you want to go to 100. Okay, what are we going to do? The ALU, so this is just a description of what we're going to see over here, but it's easier if I just show you the picture and describe it. So here's your branch instruction. I pulled this off the internet, so it's a little bit prettier. I don't know if I do view, if you'll see it better. Let's see. Is this going to work? Is that better? Yes?
Yeah.
Okay.
Yes.
Good. Okay, so here you see, one problem is I'm going to close this. No, I want to put here. Okay, so here again, we see that same register. This is what we're calling the instruction register. Very important. That's where the line of code that I want to execute at the moment is going to be stuffed into. It's just stuffed right in there. The opcode is here. That's the leftmost, the most significant bits. And we're ignoring them because we presumably know that we're in a branch instruction. So the RS and the RT are the only 2 registers we're dealing with. And now, okay, here's a little bit different. instead of the RT being connected to the right register down here, which we don't even see in the picture, it's going to be connected now again to the second address, second source register, just like an add command. Now we're using the railroad tracks of the add command, even though it's not an add command. We're using those ones because we want the first two registers to go straight into the two source registers. Then we are going to read out the contents of those two registers, because those are the two registers, remember, that we want to compare if they're equal or not. So we're getting out here, let's say some 32 bits, which is some value, let's say 1,000,000. And over here, we're getting out 1,000,001, for all we know. Getting our 2,000,000. We're getting some other value. That number goes into the ALU, and what? And compare. It says compare to control. Compare to branch control. Well, this is actually going to go to the controller. This result, because remember, if it's 0, we're going to do subtraction over here to compare if they're equal. If this is 1,000,000 and this is 1,000,000 and we subtract, we're going to get 0 over here. If we're not, we're going to get some number over here. And actually, there's a special flag. I don't know why they didn't draw it in this picture. There's a special flag, another outline. There's two outlines for or maybe that's what this line is. There's two outlines of the ALU. One is the regular result. In other words, if it's 1,000,000 and 1,000,000, if it's 1,000,000 and 2,000,000, and I'm subtracting, let's say 2,000,000 minus 1,000,000. So then I'll get 1,000,000 out on this line. And that line we're not interested in. So maybe they didn't draw it. We're not interested in the result of the actual subtraction. We're just interested in, is the result 0 or is it not 0? So we have like a special line that comes out of the ALU, which is called the 0 line, which just tells us yes or no, is it 0?
Why do we output the other line if we don't actually need it?
Because it's built there. Remember, this is the same ALU that I'm using for an add. So I have to have the line that gives me the result. It's just not drawn in this picture because it's irrelevant to us at this point. If it's an add, then it would be relevant. But again, we have the same physical hardware. We're just highlighting those lines that are of interest to us. So here we're interested in the special line that tells us whether it is 0 or it isn't 0. And that line is going to go to the controller. And the controller is going to decide whether to what to do with the PC. Should the PC just go up by 4, like it normally would, because the two values are not equal? Because remember, this is if it's equal, then jump. If it's not equal, then just go to the next line. So the controller has to decide whether he's interested in going to the normal PC of +4 or some other PC. Now, what is that other plus PC? Well, you got to take these 16 bits. This is the branch location, but it's 16 bits. So the first thing we do is sign extended and turn it into 32 bits. So now we got 32 bits of that number. So if it was like 100, it'll be a lot of zeros in front. Now we shift left 2 spaces. Why do we shift left 2 spaces? Can somebody tell me?
Multiply it by 4, so it's a word and not a byte.
Exactly.
Sorry. Yeah.
And also to save, and also that way we got 18 bits of meaning instead of 16 bits of meaning. Right. So we're gonna have to multiply by 4. It's always gonna end in 4 anyway. So if it was 1 over here, we're gonna get 4 over here. But that's not what we really want to do. We don't want to jump to location 4. We want to jump to location 4 relative to where we are. Remember, you branch forward or backward from where you are. So we're going to take the PC +4, from which we already calculated, and we're going to put it in here into the add. And if this was 1 and this was 4, we're going to do PC +4 plus another 4, and we're going to get PC +8 out here. And that's going to be the location we want to jump to. So notice, by the way, that you already have the +4, because that makes a lot of sense. You're never going to jump
The
to the
plus
next
4
forward.
is like the 2 zeros at the end?
No, PC plus 4. Remember, we always increment the PC anyway because
Oh, okay.
we want the PC to be set already to the next command. So if we want to jump one line forward, that doesn't mean the next line after the branch. It means we want to skip the next line after the branch. We want to go one more forward. So it's plus 8. So that's exactly what we're going to get here. We're going to do PC plus 4 plus another 4. If we wrote 1 over here, that means we want to go 1 forward. Well, the normal behavior would be to go to the next line. If we want to go 1 forward, that must mean we want to go 2 lines ahead. So that's what we're going to do. PC plus 4 is already that 1 line ahead, plus another 4 is going to be 2 lines ahead. So we skipped over exactly 1 line. Right? It would be meaningless to skip to do a branch to the following line because then you're already going there anyway. I've actually seen people write that in their code by mistake. They write branch to the next line. But that would mean that whether the branch is true or not true, you're going to get to the next line. So it's a meaningless question. It's a meaningless branch. So anyway, again, if he writes 1 here, is going to be PC plus 4. It'll be PC plus 8, which is essentially not the next line, but the line after next. And that will go to the branch address. Now this diagram is not really complete, but notice, by the way, it's based on the book of Patterson and Hennessy. But it's not really complete because now we basically have to decide the controller, we didn't draw it, but the controller is going to decide based on this 1 here, whether it's 1 or 0, whether to jump to the address calculated over here, or which in case, if it's true, it's going to go to this one. If this is not 0, in other words, sorry, if this is 0, if the line 0 is, if the 0 line is 1, that means it was 0, and then we should go to this branch. But if the 0 line is 0, then that means it was not 0, and then we'll go to the regular PC plus 4, and that's not in the diagram. Is that clear? Are there questions? Let me just see what the next line is. Is that the end? Ah, that's the end. Good. So we finished chapter 3. And that's all we're going to explain. Obviously we could go through every single instruction and explain how it works. But we've basically shown you enough to understand the idea. You have we did an I type, and we did 2 I types, and we did an R type. We didn't do a jump. The jump is simpler. All right, I'm gonna stop here so you have time for your next class.
We're not meeting again today, are we?
No, because the lab would be today, and Weinman said there's no point in doing the lab by remote. You guys should use the time though, I think, as I said, to work on the assignments that you can. I'll try to post.
But
Yeah.
suppose we don't manage, is there gonna be like time to make it up once we eventually get back into like a real room?
Yeah, they're gonna have to work out something. Yeah. Maybe we'll have I don't know exactly how it's gonna work out. We'll have to figure out something. But yes, there will be.
It's not the end of the world if we can't figure out everything now.
Not the end of the world. No, it's definitely not required at all. But I just my opinion is that you should do it as much as you can.
Mm-hmm. Okay, thank you.
Is it going to be a way to give in the homework?
Same problem. I need to check it myself with you. So we're gonna wait. Hopefully after Pesach, the world will resume its normal course, and then I can do that. But until Pesach,
I mean, we can do that online, can't we? Can't we do that online? I'll like email it to you or something, and then you can.
No, I need to orally. I mean, we could. We may end up doing that, but theoretically, it's supposed to be an oral exam for each homework.
Right. I mean, we could talk like on Zoom.
I'm not going to contact each one of you individually and ask you questions. It's insane. I'd have to individually, in a private conversation, talk to each one of you over Zoom. I could do that, but I'm not going to do it. I've actually had tried it because I had students who were like living in Haifa, and no, I'm not going to do
We can do in pairs.
You can do in pairs. You can do in pairs. Wait, what happened? I did stop share. Oh, but now what about recording? Ah, here, stop.